All right, ladies and gentlemen, welcome to the second half of our exploration of similar triangles here. Now we're going to be focusing primarily on right triangles. In this particular diagram, let's take a look at this here. So we have our standard right triangle here. AD is an altitude drawn to hypotenuse BC of right triangle ABC. Show that angle C is equal to DAB. Okay, that seems pretty fair. Alrighty, so the thing to note about this is that first off, this is a right triangle, so therefore this is a right angle up here. We know that BC is a hypotenuse, and AD is an altitude. We know that altitudes are create right angles with the sides that they intersect, so these are right angles as well. Okay. Now we're asked to show that C is equal to DAB. All right. The hint says to let angle C be X. Sure, I can do that. Alrighty, so now we take a look at this here. We notice that this angle X is actually in two triangles here. If we look at triangle ADC, I've got a right angle here and an X. So that means this angle DAC here, this angle has a measure that's equal to 90 minus X, right? Because we know that DAC plus angle D plus angle C sums to 180 here. So as a result, we can kind of put all these together and therefore say that's the case here. Okay, that seems pretty fair. So in this case, DAC is 90 minus X. I'm actually going to use a different letter here. I'm going to call this Y here with the reminder that X and Y sum to 90 degrees. So as long as I remember that, I'm going to use these terms here. So that's a Y, that's an X. Okay. Now wait a minute. BAC here is a right angle, so that's Y, and we know that X plus Y is 90, so therefore we know that angle BAD here is X, right? And if you think, well, that's exactly what we wanted, right? We had to show that angle C was equal to DAB, and we did that here, so therefore that's X. Now, we can also finish the problem here a little bit more. We can kind of keep going here and show in this situation here we have angle B on the bottom here. So angle B does the same thing here. This is whether you have triangle BAD or ABC here, and we have a 90, an X, and therefore the other angle is 90 minus X, i.e. it's Y. Okay. So the first thing to note here, ladies and gentlemen, is that we have a bunch of angles that are all congruent to one another. Whenever we see congruent angles, especially with triangles that are layered within triangles here, we got similar triangles. So in particular, we can see here that there's a bunch of similar triangles. And so one thing I'm going to do about this here to make this a little easier for ourselves is that these triangles, they're layered within one another. To make them easier to see, what we're going to do is we're just going to draw them so they all look the same. So in particular, here's triangle, I'm going to model it after triangle ABD. Notice there's a right angle here. We have a blue X on top and a red Y on the bottom. So what I'm going to do is I'm going to redraw all the triangles that have this spread of angles, a right angle, an X, and a Y. Well, triangle ADC does that too, right? So I can go ahead and draw this here. There's a right angle here. Here's a blue X and a red Y. Okay, and then we can do this one more time. Now for the big triangle here, right? And we have this yet again. Here's our red Y. Here's our blue X. Okay, ladies and gentlemen. So now my triangles look something like this here. And of course, let's just make sure that we match our vertices correctly. So this is our middle triangle. We see that C is associated with the blue X. So this is a C up here. And we have A in the corner with the red Y over here. And here's D. And now for the big triangle here, we had C on top because that's where the X is. The Y is with B like that. And here's an A over here. So note, ladies and gentlemen, what I now have here is an important thing to note. We now have the fact that triangle BAD is similar to triangle ACD is similar to triangle BCA. So note that drawing this altitude here at the start, drawing this altitude here actually generated ourselves three similar triangles here. And that's going to be really important, three similar triangles as such. So now, because we have similar triangles, we can go ahead and write out proportions involving the sides here. So I'm going to go ahead and write some proportions involving the sides of the triangles here. So we're going to look at these two at a time. In particular, I want to write here, for instance, we can write that AB corresponds with AC, AB over AC equals AD over CD, and that's equal to BD over AD here. It looks great, right? So for this pair of triangles, we can write that. So this is for the first two triangles. Now for the second two triangles, we can do the same thing here. We can write AC is to BC here, and that's equal to CD to CA, and that's equal to AD over AB. And that's for the second pair of triangles here, right? And we can do the same thing for the third pair. One more pair, which is the outer pair of triangles, first and last. I know AB matches with BC here. Similarly, AD matches with AC here. And we have BD matching with AB here. Great. So this is our key with this situation here. Now, we have 9 fractions and 3 neat trios here. Okay, what I'm going to do is I'm actually going to focus on very specific things here. First things first, I'm going to knock this one out. You'll see why in a bit. Similarly, over here, I'm going to knock this one out. And this final one here, I'm going to knock the middle one out. So I'm going to knock those out and just focus on what we see here. The reason I knock them out is, well, take a look at what's going on here. We can go ahead and write this out. So we can write this here. Notice, ladies and gentlemen, I can write this as AD over CD equals BD over AD here. Similarly, over here, I can write this as AC over BC equals CD over AC. And over here, in this third one, I can write this as AB over BC equals BD over AB. Now, why do you think I knocked out the 3 ones I did? Well, if you take a look at what's going on here, ladies and gentlemen, you'll know, wait a minute, there's matching pieces here, right? Notice how each of these has a matching piece. AD is matching here, AC is matching here, AB is matching here. So let's focus on the first one. So this first one here, we see AD over CD equals BD over AD. So let's look back at our big triangle here. Well, let's see, we have AD, so AD is this, right? AD is the altitude here in the big triangle, right? That's the altitude we drew originally. And then CD and BD, well, they look like the pieces of the hypotenuse here. So that's going to be important to us. So notice that we seem to have what's going on here. So the pieces of the hypotenuse here, right, we can call them, let me call them left and right here. It seems like I can write it like this here, that AD, the altitude, this is going to be an altitude here, and this is going to be an altitude down here. That's going to be the, we have this sort of set up here, and we have our 2 pieces left and right here. Now, you've seen this before, ladies and gentlemen, this sort of setup where you have a proportion where you have 2 things that were the same. This is our good old friend, the geometric mean, yet again. So we have our geometric mean thing popping up again. So we have this. So the geometric mean we have here, the altitude is the geometric mean of these 2 pieces here, these 2 pieces of the hypotenuse. Okay, well, I can do the same thing over here, but this time let's look at the big picture. Now we have AC. AC is the hypotenuse of one of these small triangles, but it's the leg of the big triangle here, right? I'm only looking at this in terms of the big triangle. And then we have BC, which is the entire hypotenuse, and then we have DC, which is a portion of it that's right underneath it, right? This is sort of like our piece right underneath it here. So notice how CD is attached to AC here. And in the same sort of figure, in the same sort of setup here, we have AB over BC equals BD over AB. Okay, AB, yet again, we have a leg over here. And then we have BC, the hypotenuse, and then BD is just this portion of the leg of the hypotenuse that's attached to the leg here. So we have that sort of setup. So these 2 together, ladies and gentlemen, give us another thing here. So it seems like we can say that our leg here is going to be the geometric mean of the hypotenuse, and then sort of the adjacent piece, the piece of the hypotenuse that's attached to that leg. So in this case here, notice how in this situation, right, with this leg AB, we're looking at this segment BD here that's attached. With this segment AC, we're looking at this segment here, DC, that's attached, okay? And we can summarize it in this form. So therefore, we can summarize it like this here. What is known as the right triangle altitude theorem, ladies and gentlemen. We can go ahead and write this out here, okay? So if an altitude is drawn to the hypotenuse of a right triangle, then there are 2 parts of the right triangle altitude theorem. The first part is that the length of each leg is the mean proportional, or geometric mean, of the entire hypotenuse and the segment of the hypotenuse adjacent to the leg. Okay, that's what I showed before. That was the second half here. And then the length of the altitude is the mean proportional of the segments of the hypotenuse here. Okay, so we have, again, AD here, this altitude, is the geometric mean of BD and DC, the mean proportional. And the leg, AB, is going to be geometric mean of the entire piece, BC and BD here. Similarly, if we want to do AC, this here is going to be the geometric mean of the entire hypotenuse, BC, and the small piece, DC here. And therefore, as a result, you have your entire right triangle altitude theorem here. And this is going to prove to be very useful as we move on.